And I know nothing about this wild chicken population. I am not a biologist. I'm not a zoologist. I just do math. So I am making this stuff up, folks. I am going to make up our biological model to tell us what's going on with the chicken population. So here's what I know. The rate of change for the number of chickens, that means we're taking a derivative, or rather someone else took a derivative. Our rate of change for the number of chickens, it's really hard to see that red, isn't it? New markers. Fourth time's a charm. The rate of change for our number of chickens, which I'm just going to call C prime to be more consistent with the book's notation. And I got to try to figure out my video settings here because it's doing some weird stuff. Let's see if that helps. Rate of change for our chickens. Suppose that I told you that the rate of change for our chickens looked like 5 minus C times C minus 15. And now the question is, depending on how many chickens we start within this population, how many chickens are we going to end up with? So this differential equation is giving us a ton of information, even though we don't know it yet. I am a visual person, which means I want to visualize this by thinking about it graphically. And right now, this derivative has been given to us as a function of the number of chickens. So if I go to set this up graphically, this axis right here is going to be my C prime. And this axis right here is going to be C, or the number of chickens. Well, this thing, if I'm pretending that this is like a y equals 5 minus x times x minus 15, this is some kind of parabola. And I know on this parabola that I've got intercepts at 5 and 15. So I'm going to have intercepts here at 5 and at 15. And this particular parabola, if we were to multiply everything out, would have a negative x squared term. So I know that my parabola should open down. And you're just going to pretend that's a beautiful parabola and a perfectly smooth curve. Okay, now it's time for some 17A review. Well, this axis right here is telling me what's happening with C prime. So in terms of the picture, everywhere up here, my C prime is a positive number. Okay, we can't see that. I'm just not having luck with any of my other colors of markers today. C prime is greater than 0. Now from our 17A knowledge, if our derivative is greater than 0, then we know the function's increasing. But the question is, who's increasing? Well, the thing that we took the derivative of. Since we took the derivative of C prime, that means that C is increasing, or C is getting bigger. Now, the one last step here that I need, if C is getting bigger, then on this picture, the bigger values of C are towards the right. So so we move towards the right. Now, if I go through that same set of logic down here, everywhere down here, my C prime values are negative because I'm below this axis, which means that we're decreasing which means C gets smaller, which means we move towards the left. Okay, so now that we know how the rules are going to work, somebody tell me, how many chickens are we starting off in our population with? You can type it in the chat. Pick a number, any number. I know I'm more excited about the chickens than you are. Someone loves chickens. 0. Oh, okay. Well, you know what? The biology is really easy. If we start with 0 chickens, they can make no babies. There are no more chickens. How about a number that's not 0? So biologically, it's more interesting. Cool. I saw an 8 and a 12. Any other? Well, whatever. Let's start with 8. So if I start with 8 chickens, this picture right here tells me what's going to happen to this population of chickens long term. Okay, 8 is somewhere between 5 and 15. So here's an 8. So if I start off with 8 chickens, then this curve right here is telling me what's going on with C prime, meaning it's telling me how the chicken population will change. So if I start at 8, then I look to this graph, and the graph says, okay, we're right here. If I'm right there, then on this graph, I'm above the axis, which tells me that C prime is positive, which tells me I'm increasing, so C is getting bigger, and I push to the right. So I started off with 8 chickens, but I'm going to push to the right and have more than 8 chickens. Then I say, okay, I'm right here. I've got more than 8 chickens. I look to the graph to tell me what to do. Now I'm right here. Hey, look, I'm still above the axis. C prime is greater than 0, so I'm increasing, so C gets bigger, so I move to the right. I think you can see where this is going to play out. I'm going to keep moving to the right. Now, at some point in time, if I keep moving to the right, I'm going to get exactly to 15. Well, if I get to 15, then thinking about this C prime thing, if I plug in 15 right here, I've got 0 times something. If C prime is equal to 0, then that's telling me C is not changing. So if I get to 15, I'm stuck there. I am stuck at 15. So if we start with 8 chickens, the long-term behavior is that we end up with 15 chickens. By the way, there's a special name for that place where the derivative is equal to 0. And if I get to that place where the derivative is equal to 0, then we're going to call that an equilibrium. Now, there were some other suggestions that popped up in terms of starting populations for our chickens. So let's suppose that our chicken population actually started off at 20. So 20 is over here. So if that's my starting population for the chickens, then this curve tells me how the population changes. So I'd go to the 20 and I'd come down here, and it looks like I need to continue my parabola. Okay, so I'm at 20, so I come down to the curve, and then I say, hey, I'm down here in this realm below the axis. So C prime is negative, which means I'm decreasing, which means C gets smaller, and the smaller C values are to the left. So I started out here, but I get pushed a little bit to the left. So now I'm right here. I look to the curve to tell me how that population is going to change. I'm still below the axis. C prime is less than 0. We're decreasing, so C gets smaller, so we move to the left. Well, if this trend continues, and I keep moving to the left and to the left, then eventually I get to 15. And if I get to exactly 15 chickens, then I'm stuck there forever, because C prime would be 0, so my population can't change. So it looks like no matter how many chickens we start with, we are headed to 15 chickens. Plot twist. Suppose that we actually started off with fewer than 5 chickens, like 3 chickens. Well, if I started off with only 3 chickens, then this curve tells me how my chicken population is going to change. So I'd come to the curve and I'd say, wait, I'm below the axis. So C prime is less than 0, so I'm decreasing, so C gets smaller and we move to the left. Well, now suddenly there aren't 3 chickens. There's only 2 chickens. Well, I'm down here, which means C prime is less than 0, so I'm decreasing, so C gets smaller, so I move to the left. And before you know it, my chicken population has died off. Now, technically, this graph leads to zombie chickens, but we'll get there in another problem. This right here, we can call this a phase plot or a phase plane. And this diagram is telling us what's happening over time based on this right here. Now, I mentioned that whenever our derivative is equal to 0, specifically when our population is not changing, then we call that an equilibrium. So for this particular model, we had 2 equilibria because there are 2 values of C where if we start exactly at that population, the population won't change. So our equilibria are C equals 5 and C equals 15. There's an extra word that we associate with those equilibria, and that is to talk about them being stable or unstable. So looking back here, when we started with a population that was a little bit less than 15, the population grew until we hit 15. And when we started with a population a little bit bigger than 15, the population got smaller until it went down to 15. We call that stable if moving away from that equilibrium in either direction pushes us back towards it based on the equation. So we would say that C equals 15 is stable. Looking at the C equals 5, when we started a little bit less than 5, our population moved away from the 5. It was getting smaller. And when we started a little bigger than 5 over here at 8, our population also moved away from the 5. It was moving towards the 15. So if everything is moving away from that point, then we call that unstable. Questions about my fake chickens? Here's my sea otter population, and this axis is going to be my S prime, or it's telling me how my sea otter population is changing. And my sea otter population here is going to look like this. And I'm going to say that this is 30 and 75. Now, I drew my graph going over here, but that's what I wanted to address. If this axis is my number of sea otters, then we can't really have a negative number of sea otters. Sometimes there's fun math going on over there, so sometimes I choose to call them zombie sea otters, the dead ones, the negative numbers of sea otters. But they're kind of undead because they're actually negative numbers of sea otters. That's why I call them zombie sea otters. We're just going to stick with the positive numbers so that we don't have to imagine zombie sea otters. Okay, so over here, I'm going to do the same thing, but I'm going to hit the fast forward button we did last time. So I know that everywhere above the axis, that's telling me that S prime is greater than 0. And if S prime is greater than 0, then S gets bigger. And if S is getting bigger, the larger values of S are toward the right. So we're moving toward the right. Everywhere down here, I know that S prime is less than 0, which means S is getting smaller, which means we are moving toward the left. Now, rather than picking some particular starting populations of my sea otters, I'm just going to dive in and look at overall what's happening in the population. So anywhere that my curve is below the axis, I know that those are places where my S values are getting smaller and I'm getting pushed towards the left. So if I think about my possible S values, everywhere in here, I'm going to get pushed towards the left. So any starting position for the number of sea otters in here, sad for sea otters, they're going to die out. Also, if I start with any number of sea otters out here, I'm going to get pushed towards the left. In this realm, because everywhere here, my S prime curve is above the axis, so S prime is greater than 0, so S gets bigger, so I'm moving towards the right. So everywhere in here, if I had an initial starting number of sea otters, I would get pushed towards the right. Now, one of the things that you aren't necessarily going to get asked to do, but it is something that might get talked about in class, or if you're reading the book, it's certainly gonna come up, is this actually, if we think about it, biologically makes sense for a lot of populations. Well, first of all, I would argue that 0 being an equilibrium point always makes sense. If I have no critters, they can make no babies. So 0 should always be, from a biological standpoint, if we're talking about population dynamics, 0 really ought to be an equilibrium. Now the next thing here, 30 is an unstable equilibrium, because if I move away from 30 just a little bit, I get pushed further away from 30. Sometimes we talk about that 30 as a critical threshold or a critical mass. So for this population of sea otters, if there are fewer than 30 sea otters, the population dies out. There are a lot of different environmental factors or genetic factors that might make that make sense from a biological modeling perspective. Now, this next one, the 75, we often refer to as a carrying capacity. This stable equilibrium is giving us the maximum threshold that this population can sustain. If we get above 75, then these population dynamics are going to move us back down towards 75. But as long as we've made it over that critical threshold, then any number of sea otters in here above that critical threshold, that population is going to build up to that carrying capacity. So just to recap from looking at the graph, I know that this is a stable equilibrium, and I know this is an unstable equilibrium. Okay, so far so good. Questions about sea otters before we talk dolphins? Great. Before I erase this, I want to point out something that's happening mathematically on this graph. When I'm at this equilibrium point, if I think about the slope of the slope, meaning this function here is already the function S prime. When I'm at that unstable equilibrium, then that slope as I go through that point is a positive slope. Positive slope as I'm going through that point. When I'm on that stable equilibrium, I've got a negative slope as I'm going through that point. And that's always going to be the case, because in order to be at a stable equilibrium, I know that on the left-hand side, I'd have to get pushed to the right. meaning on the left-hand side, the curve would have to be above the axis. And on the right-hand side, if it's going to be a stable equilibrium, I need to get pushed to the left, meaning on the right-hand side, I'd be below the axis. So that's always going to lead to an equilibrium point where the slope of the slope is negative. So when we talk about the dolphins, we're going to do this not graphically, but we're going to do it analytically. Erasing stuff. And if I seem overly excited, this really is like my favorite part of the book. So apologies. D is going to represent the number of dolphins in some wild pod of dolphins. I think that's what we call a group of dolphins. So let's say that our population of dolphins follows that D prime is equal to 2D minus 3D squared. And what I want to know, without sketching a graph, I want to find all equilibria and determine their stability. Well, finding all equilibria, that means I'm looking for the places where my derivative is equal to 0. Or even if we like connect that word equilibria back to maybe context you've seen it in chemistry, when we're at equilibrium, things aren't changing. So when I'm here at equilibrium, my D is not changing. My population of dolphins is not changing. I chose something where I could easily factor it. So I'm getting 2 minus 3D is equal to 0. So D equals 0 is one equilibrium, and D equal to 2/3 is our other equilibrium. Okay, now we got to talk units for a second. Nobody wants to see what 2/3 of a dolphin looks like, right? But suppose that this was the number of dolphins in hundreds. Okay, now we're not talking about 2/3 of a dolphin. We're talking about 2/3 of 100 dolphins. Okay, yeah, that still worked out messy. 300? No. Anyway, don't get hung up on the numbers. Don't think about 2/3 of a dolphin. Really, it's a large population. Okay. Now that I have our two equilibria, I need to determine the stability. Well, when we do it graphically, we're looking for those places where as we come through the axis, either we have a negative slope and it's going to be stable, or a positive slope and it's going to be unstable. So we need to find the slope of the slope. In other words, I need to take the derivative of our D prime. So if I treat my D prime as some new function and I'm just going to call it F, then I need to know what is F prime. Well, my derivative here, I'm looking at 2 minus 6D. Now, at each of those equilibria, what's the value of F prime, or what's the slope of our slope? How is our population changing? So F prime of 0 would be 2 minus 0, or 2. That's positive, which makes that unstable. And when I look at F prime of 2/3, I'm looking at 2 minus 6 times 2/3. 6 over 3, that's going to turn into a 2. 2 times 2 is 4. 2 minus 4 is going to give me a -2, which is less than 0. So this is stable. So that tells me that the long-term behavior for this dolphin population, no matter how many dolphins we start with, as long as it isn't no dolphins, this population is going to survive. Because 0 is unstable, and we do have a stable equilibrium here at 2/3, that means whether we start with more than 2/3 or less than 2/3, either way, in the long term, we're going to head towards 2/3. So the long-term behavior for this population would be to tend towards 2/3 of 100 dolphins. So the number of dogs here is the way that my population of dogs is changing is proportional to the number of dogs in my population times 1 minus n over 50. So there are a lot of questions that we can ask ourselves, but the question that I want to answer is, if we start with 10 dogs, how many will there be after a really long time? I mean, assuming that this population dynamic stays with us. So there are a couple of different ways we can approach this. I'm going to go graphical to start, and then we'll see how much time we have. So to start with, I do want to find the equilibria so that I can get a graph of this going. Thinking about looking for the equilibrium, I'm going to set this equal to 0. Well, 3 is never equal to 0. The n can be 0. And in here, maybe you can see that n equals 50 is our answer, but we can also do that algebra a little more in slow motion. I can move my n over 50 over and then multiply both sides by 50. So n equals 0 and n equals 50 are my two equilibria. Here's 50, and we know it's a parabola that points down. Again, I probably don't want zombie dogs, so I'll go ahead and just stop that at 0. So here's my D. Oh, I said D was going to be our population of dogs, and then I used N. Sorry about that. We'll just go back and put that in as N, habit. So dN dt and N. So already just thinking about my picture, I know in this whole region, because my curve is above the axis, everywhere in here, that dN dt or n prime is positive, which means n gets bigger and we move to the right. Everywhere down here, my n prime is negative, which means n is getting smaller and our smaller n's are toward the left. So in this portion of the curve, I know I'm getting pushed to the right. And in this portion of the curve, I know I'm getting pushed to the left. So I can pretty quickly answer this question of if we start with 10 dogs, so if I start right here, then I know I'm going to get pushed to the right and end up at 50. So that long-term behavior is that we're going to end up with 50 dogs. But I want to explore this a little more carefully. So this is all well and good, but it's not the way our brains are usually used to thinking about graphs, where this axis is my derivative. And if this is like a y prime, this is like a y on my x-axis, and all of that is weird. So I instead want to think about what that means for my population as a function of time. That's a little bit more normal in terms of how we might think about our axes being laid out. Well, here I told us that we're going to start with 10 dogs. So when t equals 0, we're going to start with 10 dogs. And we've already figured out that after a really long time, we know we're going to get pushed to 50. So if that's 10, I'm just going to call 50 up here. And at some point in time out here, we're going to get to 50. But the question is, how do we get to 50? And a lot of that is hiding in this graph for us. Up here, at the maximum value on this curve, I know that that slope is equal to 0. But it's not the slope in the sense of the derivative of n, because this curve is already n prime. So if the slope up there is equal to 0, it's like the slope of the slope. Or I can think about that as telling me n double prime is 0. It's not quite right. We need a little bit more from 17c before we can really say that. But it is the derivative of the derivative being equal to 0. Thinking back to 17a, if I take the derivative of the derivative and it's equal to 0, then that's an inflection point. So this right here represents an inflection point on this graph. Since it's a parabola, I know exactly where that 0 is, because I can find the vertex of a parabola. It's halfway between these. So that's going to be at 25. So I know over here that at an n value of 25, so that's 50, halfway up, so at an n value of 25, I should have an inflection on that curve. Now I'm almost ready to finish that off, but there's one more thing that I want to talk about here. So this right here is a graph that's telling me something about my slope, because it's telling me about dn dt. And I know everywhere in here, again, because I'm above the axis, I've got positive slope. So when I come over here, I know that when I start at 10, I need to start with a positive slope. So my population is going to be increasing. And then we're going to get to that inflection point of a population of 25. And rather than being that nice concave up thing, we're going to hit that inflection point and suddenly be concave down. And that long-term behavior is that I'm going to be asymptotically approaching 50. You might have seen this curve before. This curve shows up so often in our biological models that it's got a name, and this is the logistic curve, or it represents logistic growth. And that idea of logistic growth, anytime we're seeing this growth pattern where we start off with pretty significant growth, and then when we get past a certain point in our population, then that growth rate starts to slow down, but continues to reach some sort of carrying capacity.